Hello everyone, my name is Silviu Grigore and I am a software engineer at Fitbit, which is now part of Google. Today I will be talking about firmware updates on Fitbit devices, but first I want to say a few words about myself. So, I am a software engineer passionate about low-level programming, and I have a background in compilers, networking, and embedded systems. As a member of the Fitbit Tracker platform team, I have been working with Nadix for the past 2.5 years. My work revolved around firmware updates, comms, and data acquisition from various sensors that we are using on our devices. So today I will talk about the firmware update process on Fitbit devices that are running Nadix. So we will first describe the flow for our initial implementation of firmware update, which is done in foreground. Then we will discuss about the limitations of this approach and the optimizations that we did to improve the user experience. One of these improvements is trickle update, which is downloading chunks of the update in background, and another improvement is delta update, which is sending binary diffs instead of full update files. In the end, we will draw some conclusions. So we will start the presentation with the foreground firmware update. First of all, what are we updating on our trackers? Um, First, the bootloader and the operating system image. Second, the system assets, which include fonts, translation tables, and images that are used by the user interface. The system assets are split into local independent assets, which are common to all languages, and locale dependent assets, which are used to support a specific language. We are also updating the application code and application assets and the firmware images for those peripheral components that are running their own firmware. Example of such components on Fitbit devices are the NFC, the GPS, and the touch. So how is the update packaged? The update is packaged as a collection of files which are called bundles. The update files are using the ELF format, which acts as a container for the raw image. Besides of the raw image, the bundle includes some metadata which is used by the firmware update process. So we have one file for the bootloader and the operating system image, one file for the locale independent system assets and one for the locale dependent system assets, one file for each application, and one file for each peripheral firmware image. The bundle files are generated by the build system and they are uploaded to the server, which delivers them to the devices. So how is the update delivered? We have a Fitbit application which is running on a mobile device. This application is used to connect to the Fitbit ecosystem, and it includes device pairing, synchronization, firmware update delivery, and many more features. Um, the users log into this application with their Fitbit account, and they pair the Fitbit device with the application through BLE. When a new firmware update image is available, the user receives a notification in the Fitbit application, and when the user initiates the firmware update from the application, the mobile device connects to the server through either Wi-Fi or mobile data. Um, it requests the update image from the server and it sends it to the Fitbit device through BLE. for security reasons, the firmware update image is encrypted end-to-end between the server and the Fitbit device, and the mobile device only acts as an intermediary. Also, in case something goes wrong with either of the two connections, a resume mechanism was implemented to avoid downloading the entire image again. Um, how is the update installed on the device? We are using two special RAM levels to free up some RAM memory and to avoid interfering with other tasks. So these RAM levels are closing all the unnecessary tasks, including the UI. We have only minimal UI while downloading and installing the bundles. And we have an OTA RAM level, which is used for bundle downloading, and a firmware update RAM level, which is used for bundle installation. We have a two-step install process preceded by a preparation step. In this preparation step, the bundles are validated, and the bootloader is configured to install the bootloader and the operating system image, and the system is rebooted. Upon reboot, the bootloader is installing the image and it's rebooting the system again, and then the system is booting up the new OS image, and it is installing the system assets, the applications, and the peripheral firmware images. So as we can observe in this diagram, the update is installed to the internal flash, external flash, and the peripheral devices. The bootloader image is installed only in the internal flash. The OS image is split between the internal flash and the external flash, depending on the importance of the code. The system assets and applications have two parts: metadata part, which is installed on the file system in the external flash, and the ROMFS image, which is installed in a specific application slot partition. The peripheral bundle contains some configurations that are installed in the file system, and the firmware image, which is installed on the peripheral device. Due to space constraints, um, the update bundles are deleted after the installation. Now that we saw how the bundles are downloaded and installed for the foreground firmware update approach, let's talk a bit about the limitations of this method. So first of all, because we are using the two special run levels that are keeping alive only the tasks that are essential to the firmware update process, the device cannot be used during both download and installation steps. Also, doing large BLE transfers increases the probability of a disconnect, and re-establishing the connection introduces an additional overhead. This disconnect may be caused by incompatibility with the mobile device BLE chip, uh, poor connectivity due to interferences, or user simply not keeping the Fitbit device in the proximity of the mobile device. Also, multiple disconnects may lead to aborting the update and starting it from the beginning, in spite of the resume mechanism that we have implemented. In order to speed up the download, the device is running in a high power mode, which leads to faster battery draining. Now that we discussed the limitations of the foreground update approach, let's see what we look for from potential improvements. First of all, reducing the duration of the BLE transfer, which will lead to a lower probability of seeing disconnects that may trigger restarting the update from zero. Um, Reducing the duration of the BLE transfer will also reduce battery draining during the update. And this is very important because we need the battery to be above a specific threshold at installation time in order to perform the installation in a safe manner and not risk breaking the device. Another improvement point would be to also reduce the overall time during which the device cannot be used, which is directly affecting the user experience. Okay, so let's talk about our first improvement, which is trickle firmware update. In order to be able to explain the trickle update mechanism, we will first introduce the device synchronization process. The device synchronization process is using the same um, infrastructure as the foreground update, but it differs in the data exchange between the server and the device. The mobile application is still acting as an intermediary, and the data is still encrypted end-to-end between the device and the server. But right now, the device is sending sensor data and logs to the server, and it's receiving configurations and process data from the server. Synchronization can be initiated in the mobile application by the user in foreground, or it can be done in background every 15 minutes if this feature is enabled. The background synchronization requires a BLE bond with the mobile device, and the Fitbit device needs to be in range. So how is the update delivered? First of all, the update is packaged the same way is done for the foreground firmware update. Um, the difference is that instead of downloading the full update at once, the update is split in chunks, which are downloaded during background synchronization. The size of the chunks is configurable, and it should be small enough to not introduce a significant overhead in the background synchronization process, leading to problems similar to those encountered during the foreground update. Also, because we don't want to wait forever for an update to be delivered chunk by chunk, we implemented a configurable time window during which the update chunks can be delivered. When this window ends, the rest of the update is downloaded in foreground. Okay, so let's discuss about the advantages of this approach compared to the foreground update. So packaging and installation is the same as for the foreground update, but the BLE transfer time is reduced because the update is now split into smaller chunks which are delivered during background synchronization. The time while the tracker is unusable is reduced, um, and in the best case, only the installation is done in foreground. Okay, now regarding the limitation of this method, um, delivering the update takes longer time, days, maybe weeks from the moment the update was released. Also, it's highly dependent on users' behavior because the device has to be connected all the time for the update to be transferred quickly. And in the worst case, when the device is not connected during the update time window, it will revert to full foreground update. Also, devices using Trickle have to reserve in the file system the space needed to store the update bundles. This is not required for the foreground update because device synchronization is forced just before starting the bundle download. And this way, the space that was previously occupied by the sensor data and the logs that were uploaded to the server during device synchronization can be used to store the update bundles. So now that we saw how trickle update is working, we can go to the next improvement that we did, which is Delta firmware update. First of all, how is the update package? It's now a mix between bundles and patches. Um, we are still using bundles for peripheral firmware images and patches for bootloader and operating system image, system assets, and applications. Due to the space constraints that don't allow us to keep the current builds bundles, in order to be able to recompose a bundle corresponding to the new build with the data that we have on the device, the diff is computed between the current build's raw image and the target build's bundle. So we are still using full bundles for the peripheral components for because for various reasons they don't allow us to read their firmware image. One example would be the NFC device whose firmware image can be read due to security concerns. Let's talk about the format of the patches that we are using. The patch format is binary and it includes a header and the data. The header part contains a magic value which is used to identify the file as a patch, and the patch version which allows extending the format in the future. It also includes the target bundle type and the data needed to retrieve the raw image from the flash. For the bootloader and the operating system image, it includes the internal and external flash mapping, and for system assets and applications, it includes a universally unique identifier. The data part contains the diff between the raw image and the bundle. Now let's discuss about the diff format. We're using the BSDiff algorithm for diffing and patching, and the LTG algorithm for compression and decompression. The requirements used during selection of diff and compression algorithms were the following. We search for algorithms that are generating significantly small patches. We are able to generate patches that are between 4 and 50 times smaller than the target bundles. We were also looking for algorithms that were easy to understand and port to an embedded environment. And we were looking for projects with a permissive software license. A few words about BSDiff. Um, BSDiff was developed by Colin Percival, and it's a block move algorithm. Um, it was optimized for executable files, and it's aiming to get the minimal patch size. Since the diff is computed on the server, which has enough resources, in this presentation we will be focusing on patching, which is done on the device running in a constrained environment. BSDiff uses a binary format consisting of a header and a bunch of blocks that include commands and data. So the header contains the magic value, which is used to identify the file as a BSD patch and the size of the target file, and then the stream of blocks, and each block has a fixed part which contains the bytes corresponding to the three commands, um, patch, copy, and skip, and a variable part corresponding to the data associated with the patch and copy commands. And let's see how these commands are working. The patch command is reading the same amount of bytes from the current offset of the patch in the input file. It sums them up and it writes them to the target file. The copy command reads a specific number of bytes from the input file and copies them to the target file. And the skip command updates the offset of the input file to ignore a specific number of bytes from there. Next, we will discuss about the LTG algorithm, which is a variation of the LZ77 lossless data compression algorithm, which was developed by Abraham Lempel and Jacob Ziv. So this algorithm is using a sliding window um, to look back for patterns in the input file. These patterns are encoded as commands in the output file. Um, the compression ratio of the algorithm depends highly on the size of the sliding window, because a larger sliding window allows finding more and longer patterns, resulting in a better compression ratio. The archive format is binary, and it consists of a header and a stream of commands and data. So the header contains a magic value, which is used to identify the file as an LTG archive, the size of the original file, and the size of the target file, and an optional checksum of the original file. It also includes the method used for decompression, which can be either LTG or plain copy. In case of the LTG method, it will also include 4 markers, which are the 4 least frequent byte values in the original file. These markers are used to encode the commands, and they were selected in such way to minimize the number of escape sequences for the marker literals. The rest of the archive is composed of a stream of commands and data. In case of a non-marker or an escape marker, which is basically a marker followed by a 0 byte, the value is simply copied from the input file to the output file, and the actual commands are copy commands, and there are 4 of them, and each is preceded by its corresponding marker value. These commands are used to copy to the output file a specific number of bytes from a particular offset in the same output file. The commands are differing in the size of the copied blocks, offset, and length. So now that we know how the patches are generated, let's see how is the update delivered. The patches are computed on the server, and the same foreground update mechanism is used, except that now the server is sending a mix of bundles and patches instead of only bundles. If patching fails for a specific file, we count the number of failures, and when a threshold is exceeded, the device will request a bundle for that file on the next update retry. Also, the device will request bundles for the firmware images corresponding to peripheral components. Um, upon a retry, um, so for all the files for which patching worked fine previously, the device will still be receiving patches. So how is the update installed? We added an additional step to the foreground installation process. This new step is iterating through the list of patches and bundles and is identifying the patches by looking at the manifest received from the server or at the magic value from the file. The list of patches is sorted in descending order by the patch size, and we do this to minimize the total size of the update files while applying the patches, given that each patch is deleted immediately after applying it. And once all the bundles are generated, the installation continues normally. So previously we said that the patches are applied over the raw images. This diagram is pretty similar to the one from the installation slide, except that the direction of the data is different and the peripheral component is lacking because it's not supported. Also, here we are talking about raw images instead of bundles, and the bootloader and the OS image is retrieved from the internal and external flash using the mapping included in the patch. Um, the application and the system asset images are retrieved from the external flash file system and partition slots using the identifier included in the patch. The identifier is used to determine the slot number, and then based on this slot number, the address of the slot is retrieved from the partition table. All these raw images are loaded with the help of character device driver that allows reading the contents of both internal and external flash. We will now detail the changes that we have done to BSDiff and BSPatch, which is the patching component of BSDiff, and LZG in order to use as little RAM memory as possible. We didn't have to do too many changes to the diff and compression implementation because they are running on the server, which has enough resources. We only did a small change to compression to reduce the sliding window size in order to trade compression ratio for RAM memory consumption at decompression time. First of all, we had to implement support for streams in both BSPatch and LZG because the original implementation was loading the entire input files and generating the entire output file in the RAM memory. This means that both BSPatch and LZG had to be modified to work with fixed size buffers and keep the patching and the compression state. The original BSDiff and BSPatch implementation was using the bzip2 algorithm for compression and decompression, but it wasn't feasible to port BSD2 to our constrained environment, and we had to integrate the BSPatch and BSDiff with LZG, and also we optimized the sliding window buffer of LZG to work as a circular buffer which is shared read-only with BSPatch. In this diagram, we can observe the entire patching and decompression flow. So the patch file is passed to LTG, which does decompression on demand. The character device driver is configured to retrieve a specific raw image for a specific component and is passed to BS patch, which is generating the target bundle file as an output. The flow is the following. LTG reads the data from the patch file until it fills its input buffer or there is no more data in the patch file, and then LTG consumes the input file by doing either literal copies from the input buffer to the work buffer or by reading commands from the input buffer and do the associated copies from the work buffer to itself. This is done until the work buffer is full, and then BS patch consumes all the data available in the LTG work buffer by executing the BSDiff commands. So the patch command reads the data from the character device driver to the BS patch work buffer, and it sums it up with the data from the LTG work buffer, and the copy command simply reads the data from the character device driver and to the work buffer, and the skip command simply updates the file offset of the character device driver to ignore some data. When the BS patch work buffer is full, it's written to the output file, and when the LTG work buffer is consumed completely, LTG fills it again, and this way BS patch can continue the process and so on. So what are the advantages of this method? First of all, the duration of the BLE transfer is reduced up to 10 times, which translates to a smaller probability of a disconnect and reduced battery draining. Even though the patching step adds to the installation time, the overall update time is significantly smaller than foreground update, half the time in some cases. This means that the device is unusable for a smaller period of time, improving the user experience. And now the limitation of this method. Um, First of all, it will revert to a foreground update if the raw images are corrupted, but this is very rare. The size of the update is variable depending on the differences between the two builds. Also, the additional patching step increases the installation time. Peripheral components are not supported for Delta update because they don't allow reading the firmware image, but this could be done if we save the current image on flash, but we have to reserve the space for it. And another limitation would be that the server has to compute and store the diffs for every combination of released builds. Okay, so we will now draw the conclusions. Foreground firmware update works well, but Trickle and Delta improve the user experience. Trickle is suitable for devices that have the space to store the update files at any time. It requires more time to deliver the update, and it depends on the connectivity of the device, but the device is unusable only during installation. Delta is suitable on any device. It adds some extra time for installation. it needs the raw images to be valid, but the update is delivered quickly. And why not use both of them? It could be possible for devices that allow trickle because we need to reserve the space for the mix of uh, bundles and patches. Also, in order to not increase the installation time for trickle, the patching step should be done in background, and this way the um, build will be delivered faster and the device will be unusable only during bundle installation. Uh, that was it. Thank you so much for your time, and I would be happy to answer your questions.